Masuk failed to teach you what I think is the most important word I would want to know in any foreign language. So let me do that task. I believe pijo?
Beer.
Beer, thank you. There we are. Okay. So, but I learned that, and I learned the character for meat, and it's really great because you're wandering around and you just see the character for meat, and you're like, yes, I'll get a meal somehow. So, yeah. Okay. So, very nice to be here again at the Polish Poor Workshop, and it was quite an easy journey over here, actually, and I'm very, very happy to be back now. What I have for you today is a talk on reactive programming. Who knows what reactive programming is? Like, a few. Okay, Liz, yeah. How do you know, Liz?
From you?
From me. Because she's implemented half the stuff I'm about to talk about. Yeah. Okay, so, well, what am I here to talk to you about today? Well, I'm here to talk to you about asynchronous data. Okay? Things like events in a GUI application. Things like signals from Unix. Things like web requests arriving, or file change notifications from your operating system, or a little timer sat there going tick, tock, okay, every second. All of this is asynchronous data. What does asynchronous mean? It means the data arrives when it damn well pleases. Okay? We don't get to choose when it comes. So this is a sort of data where stuff just comes into your program and, you know, it's like, oh, something happened. And, you know, once we start doing that, asynchronous data can become very, very interesting. So we all love Google, of course. So when you start typing something in, you get to see what other people searched for, and then you start to get depressed about humanity. But I'm glad to announce that apparently more people want to die than download WhatsApp, so it's all bad. But if you think about implementing this right, there's a bit of a tricky thing. Because what happens is, you know, we sort of sat there and we say, oh, the user typed something. Let's send a web request off to, you know, go and see what we should suggest to them. So we make a web request off to some server somewhere. And then the user types a few more characters. And we're like, oh crap, they typed some more. Okay, let's send another web request. Okay? So we send off this second web request. And this second time we get really lucky. You know, everything works out, we hit a server and it is very, very responsive. And we get back a result. And we put it on the screen. And then the first request we sent, the response eventually arrives. And then it's like, oh, what should we do? And of course, if we're not careful, we know what's going to happen, right? We're going to go and shove the old request's data into here because we just wrote some kind of callback. And, well, that's a mess. So, as soon as we start dealing with any of this sort of asynchrony, things start to get a bit of a pain. One other thing you might be wondering is, are we going to be talking about threads here? And the answer is, well, no, not necessarily, but sometimes yes. If you think about building any kind of UI application, you know, can you just go and make a heavy computation, okay, on the thread that is meant to be keeping the user interface alive? Well, if you do that, the user will be very, very, very sad. It's a little bit like if you, does anyone use the Active State tool for installing modules? It's great, you know, you say load, and it pops up, and then it's completely unresponsive while it loads and populates the module list, okay, and you can't do anything with it at all, and then eventually it comes to life. This is not what users want these days, okay, it's not a good user experience. So whenever we have sort of, you know, web requests to make, or lots of data to load, or something like that, we always want to do it on another thread, or we want to go and sort of make, say, a request asynchronously instead. And, you know, all of these things sort of draw threads in. If you go and write web applications in various tools, they're just threaded by default. Not so much in the Perl world, but elsewhere, you know, requests come in and they just get shoved onto different threads. So I'm not necessarily going to be talking about it, but of course, you know, this definitely is something that happens in an asynchronous way because we set a computation off, and when does the result come? Well, when it pleases, and then we better do something about it. So in general, these things are kind of like, argh, to deal with, okay? And I've spent plenty of my career sort of, reviewing code that other people wrote that deals with asynchrony, concurrency, and parallelism. And there's basically one thing that most of it has in common, and that's that it's wrong. So let's just sort of step back from all of the horror for a moment and think about something a bit easier. Okay? Because I think I've scared you enough already. So let's do something very, very simple. So let's look at synchrony. Okay? What's synchrony? It's where you make a call to, say a method, a subroutine, a built-in, and you get a result back. Okay? And while the work is going on to get you that result, you're just sort of sat there waiting for it, chilling out, okay? And then the thing returns you a value and you get on with it. So here we have a little bit of code that's just reading through a file. And it's actually the only bit of Perl 5 code I have in my presentation, but now you can see I can still write it. I hope it's correct. But anyway, if you sort of think about what we're doing there, we're going through the file a little bit at a time. Okay, we're slowly moving a line, a line, a line. And if it's a 10 gigabyte file, that's probably a very good idea. Now, one of the things that we can do when we have lists of things is we can start using various sort of operators that essentially process lists of things. And let's take a look at this little example. Okay, so here we get all the gold members in, for example, a frequent flyer program. And then what I want to do is grep out all those that have more than 10,000 points. Okay, and then these are entrants into a little competition. And I want to pick 10 winners, okay, from my entrance to this competition. So I pick them out, and then I want to map out the names of the winners, okay? And what on earth is this star dot thing? That's a way of writing a little anonymous subroutine block, which does the name method on $_, okay? But it looks cute. You'll see that it's actually clever enough to know that when you say star.points, it should actually shove this other greater than 10,000 into the closure as well. So this all works out pretty nice. But the thing about these, if you think about what they are, this, this grep, this map, this pick, okay, they're all about iterating. They're things that take a list of items and do something with them. And one of the things that we actually can do over in the Perl 6 world is actually have these be infinite. Okay? So here I have a sequence of the Fibonacci numbers. What are the Fibonacci numbers? Well, if you don't know, we can just read it out. It starts with a 1, and then there's another 1, and then we add whatever to whatever, okay, all the way up to infinity. And what are the whatever and whatever? Well, it's 1 and 1 the first time, so that's 2. Then it's 1 and 2, which is 3, and then it's 2 and 3, which is 5, and then it's 3 and 5, which is 8, and so on. Now, of course, if we actually, try and compute an infinitely long thing, we might run out of memory at some point. So we don't really want to do that. So I'm actually using the binding operator there, which basically says don't try and assign things. Just bind that list there. And that basically says, we really don't want to go evaluating this thing now. But once I've done that, I can actually grep them. So I can actually start finding all the even Fibonacci numbers. Okay? And then we can just print 10 of them. That's a way of writing a range from 0.9. Okay? It's like up to 10. It's kind of like the Chinese bit of Perl 6. So if we kind of think about it, we have a way of operating on these potentially infinitely long bits of data. And you're kind of looking at this now, right, and saying, well, who cares? Whenever do I need the Fibonacci numbers in my program? Has anyone actually written a real-world program that needed Fibonacci? Yeah, I thought not. However, files are actually sort of sources of data that we generally would want to work through a piece at a time. Turns out that, remember that while loop from before? Okay. Now we can just loop over the lines in the file. Why? Well, because we don't actually have to swallow them all into memory to do a for loop over them anymore. Okay? So it's lazy. Even better, we can take them and we can go and grep them. Okay? So I can grep out every line that doesn't start with a hash. We can actually use quotes inside of regexes as well, which I think is kind of cute, and then backslashes. Oh, and the X operation is on by default. Okay, so you can space stuff out. So we can think about this a little bit, and what we realize is that grep and map and sort and all of these things, we have a few more of them in Perl 6, are all about factoring out flow control. They take those places in your program where you would write a for loop and an if statement, and they say, let's write that once. And you just tell me what to filter on. Some of them get even more powerful. If we take this one here, okay, unique, what we're doing is we're getting the results from Bing and from Google, okay, to see what they found. Probably this contains useful results and this contains crappy ones. And then we want to actually sort of filter out the duplicates. Okay, so we use unique. Now, of course, if you're filtering out duplicates, you need to be a little bit stateful. You need to remember, what did they already see? So when we use something like unique, we're not just taking a loop and some if statements and so on out of our code, we're taking entire variables out of our code. So we can just think about this concept of find the unique ones, and underneath we know that of course it's doing all this sort of stateful stuff, and there's some little hash in there somewhere, but we don't need to think about it. So we can work at a higher abstraction level. So these things are kind of nice. And all of that is about synchronous data, right? This is all about lists of things where we're sort of processing the data, and the thing is that, you know, we've got these nice programming techniques for dealing with data that is just there, and we can ask for the next thing, ask for the next thing, ask for the next thing. Okay, that's what map and grep do. Map just says, give me another thing, and then it maps it and hands it off, and then, you know, something might have asked map for that thing so that it can grep it and so on. So we have these little pipelines that the data flows through. But what about asynchronous data? Wouldn't it be nice if, for things like UI events or notifications from the file system or all of these things, we could program in a similar way? If we could do that, then, you know, we can try and factor some of the recurring complexity out of doing asynchronous and event-driven programming. We can actually take different sources of asynchronous data and compose them together. So what if we want to do stuff involving both time and user interface events and web requests? That starts to get a little bit of fun. Or we can, you know, try and make it easy to deal with situations where I want to take some work, shove it off on another thread, and then have the result come back to me on the correct thread to update the user interface from. Because user interface libraries get really, really upset if you try and manipulate the UI from the wrong thread. They sort of either just do something wrong, or they work half the time, or something just, you know, segful. So if we can deal with these things, we might actually be able to make asynchronous programming kind of pleasant and kind of, you know, something you don't have to feel like you're doing, you know, a great task to actually achieve simple things. So I have a friend who's sat somewhere over there. Yeah. Hi, Carl. He comes and talks to me now and then, and he talks to me about this thing that he's learning called category theory. Now, I haven't learned enough about it, besides being able to make sort of bad Skyrim puns about it. There's actually this thing in category theory called arrows, okay? And that's why this is sort of funny. But generally when I give this, there's a maximum of one person in the room who finds it funny. And it might have been Carl, but he's seen me do this like 5 times, and it just isn't amusing anymore.
Get a new category theory pun.
A new category theory pun. Okay, I'll have to become less of a co-expert for that. But category theory is this kind of esoteric branch of math, but some people looking at various things in the light of it tend to make some interesting discoveries. And a while ago, some folks, amongst them a guy called Eric Meyer, was kind of looking at iterators or enumerators. Okay, this idea of moving through a bit of data at a time and just pulling the next item, like from a file or from a database. And kind of realized that basically it's like, give me a value, give me a value, give me a value, okay? That's the iterator pattern. Now, there's another pattern that we often sort of see in dealing with, well, if you go and read your design patterns book, for example, but particularly when you go dealing with user interface events, it's the observer pattern. And the observer pattern is kind of like an iterator that's the other way around. So whenever an event happens, it says, oh, this happened. Okay? Oh, this happened. Ah, this happened. Okay? Very exciting. So, thing is, what is realized is that all those nice things like, grep and map and zip, all these various operations that you can do on iterators, on synchronous data, you can actually define them quite sanely on asynchronous data as well. So all those things that we can do to increase our abstraction level when we're working with lists of things, be it a list of things in memory, or coming from lines of a file, or coming back from a database, okay, and we want to sort of work with them with these nice things like grep and map and so on, we can in theory do that with asynchronous data as well. And this thing got the name reactive programming, okay, reacting to things that are going on. And if we can pull this off, this is going to be really nice, because asynchronous data has, some things that make it hard. Like, it arrives whenever it wants. Heck, it might arrive from 5 different threads at the same time. Okay, that's kind of scary to deal with. But if we can nail this, we can actually factor all that nasty synchronization stuff out of our code, okay, get some poor person like Liz to get it done for us once, and then, we can just enjoy writing nice, simple, asynchronous code and not have to worry about all of these things. So, in Perl 6, the thingy that we can name a source of asynchronous data is a supply. Okay? And what do you do with a supply? Well, you tap it. So here, I'm going to create a supply. Okay? And this is an interval supply, so every second it just pushes out an ascending number. Okay, so it gives me a 0, then a second later it gives me a 1, and a second later it gives me a 2. Okay, and it doesn't actually do anything yet. Okay, that's just a supply. But if we tap the supply and we give it a little closure like this, a little block, okay, use $_ there, and what's going to happen is every second it's just going to run this thing. Okay? Now it's actually going to go off and run it on a different thread, meaning we can go and get on with other stuff on the main thread of our program. So, what's nice about this? Well, we can actually map it. Okay, it's pushing these numbers at us. So what I can do is I can just say, well, is this number modulo 2 true? If it is, say tick, tock, okay, I'll the other way around, and then we can tap this. So what I just did is I did a map, okay, on a asynchronous source of data. It's kind of interesting. It's like that map is sort of a time-traveling map, okay? It maps the future. So as these ticks come through, instead of a map being there like pulling the values, okay, so normally a map is something that sort of says, oh, there's an array, let me pull a value out of it, let me drag another value out of it. When if it's a database, we're there sort of begging, like, give me the next value, and it sort of takes ages to do so, and then it gives us it. Well, here, it's the other way around. Every time a second, ticks by, it just pushes this thing into the map, and then the map pushes it along to this save. Okay? So it's kind of a push rather than a pull. I can run that one, by the way. Here we go. There we are. Okay. That's with a reactive program. So, one of the things about this is that they don't automatically introduce threading. Okay? So if I was to actually just want to use this to just do a little bit of very basic sort of observer stuff, I can make a supply, okay, and I can tap it, be it tap, yeah, it's great, and then we can just send more values down the supply. Now there's a few other things you can do besides more. You can say done, which is your way of saying we've successfully sent all the things, and we can say quit, which means something went horribly wrong and that's an error. So you have ways of conveying errors down these things as well, and completion. So some things are an infinite supply, okay? Some things are probably not an infinite supply, so probably eventually we're out of beer, so we have to, you know, do beer.done at some point. Maybe there's an error, okay? Like they've ran out of beer or something. Not that I know anywhere that would do that. But, okay, so that's all cute, but let's actually build something interesting, okay? Let's build some kind of real thing. So I have two examples for you. The first one is about watching files. And this is essentially a source of asynchronous data, right? This is, you know, file change notifications coming in off disk, okay, and they arrive whenever they please. So if we just think about what we could build with this, I built a little tool called intercommit. So the thing about Git is that, you know, as soon as you give Git your files in a commit, okay, it keeps them. It doesn't lose them. It's happy. But if we, you know, were to sort of screw something up while we're developing, then what? So what my little intercommit tool does is we are in a directory, okay, and I say intercommit watch, and now it's watching. And then I can go and let's, do I have some files in here? I bet I do. Yeah, I have a file there called lol. Let's just echo something interesting into lol and something else, okay? And then I can intercommit list, and it will tell me there's been 2 changes to the lol file, and then I can actually just recover the states of the file back over time. And if I actually go and make a git commit, okay, like this, then I've committed, and if I intercommit list now, then the list is empty because it says, well, you committed now, so we don't need the backup anymore. Okay, so actually over in the other window, it just actually just logged what it did. Okay, so it said it backed up lol, and then head changed because we committed. So we now have thrown away the backups. Okay, so how do we build this thing? Well, what we'll do, just to get started, is we'll just start looking at when we commit. Now, the simplest way of doing that, it's not perfect, but the simple way of doing that is actually just to go and watch the head symbol, okay? And if head changes, that means that we have moved it, so we've probably committed. Or we've done a checkout, or, you know, rebased, or any of those nice things. So what I'm going to do is I'm just going to take my IO notification class, this is a built-in thing, and just say watch path, give it that path, and then I can tap the supply of notifications. So here, we can just jump out, oh my god, commit, okay. Of course, we want to do something a little more interesting than that, but we want to, for example, go and just list all the files. We use this .intercommit directory as our backup directory. So all I'm going to do is just loop over all the files in that directory and unlink them. Okay, so that's a way to delete all the backups on each commit. So how do we put them there? Well, let's take a look. So what we'll do is we'll watch it's a simple way of doing it. Just watch the changes in this path, okay, in the directory. And if we do that, we tap that and do say, and one thing you'll notice is that you start getting duplicate events out on some operating systems, okay? The problem is that different operating systems are really, really awful at giving these notifications, and they sort of say, well, we ended up writing the file and writing its metadata, so I'm going to tell you about it twice, which of course is really useless, but that's how they work. So already we're sort of in the typical situation with data, right? I mean, the data's always crap, and it happens with asynchronous data as well. So of course we don't want to make 2 backups just because the operating system sends us these 2 notifications. We better do something about this. So what we'll do is we'll unique them, okay? And we'll decide to unique them by path. That's the path of the file that changed. And one of the things that's a little bit interesting when you're dealing with asynchronous data is there's always a time aspect to it. That doesn't really happen with synchronous data when you're just pulling stuff. It comes when it comes. With asynchronous data, time is often also a very interesting axis. So what we can do here is we can actually just say, well, this unique actually expires after 1 second. Okay, so what it will do is it will remember what it's seen, okay, for a period of 1 second, and then it will actually just expire those entries, and then it'll let the thing through. So yeah.
Could you just as well have used Squish then?
Could we just as well have used Squish?
Yeah.
No. Have you ever used an editor where you can save multiple files at once?
No.
Okay, I do.
Okay, I see what you mean.
If you click Save All,
right.
There's no guarantee that our wonderful operating system won't go into leaving the notifications.
Right.
Yeah, because operating systems are awesome, especially when they're Windows. Yeah. Yeah, so unique is a safer bet for that. Yeah, good question. And with Squish, expires probably makes sense as well.
Yeah.
Do we have it? Do we have expires on Squish? Oh, well there you go. So, what we can do then here is just tap, okay, this unique source. So this is kind of nice because we've actually just done something pretty hard, but with one line of code. Okay, we've got data coming in whenever it wants, and we've made sure that for a given path we don't actually get it more than once per second. Okay, with a single line. So we can sort of scale this up a bit. So what I can do is I can I can say I want to only watch those that expire. And then what I actually get out of watch path is an object. Okay, it contains what sort of change it was and what the path was. So then I can map out just the path, because that's all I care about. And when I first wrote this, something really funny happened. Basically, whenever you put a backup file in the backup directory, the directory changed. So then it backed up the backup directory into the backup directory, which was a change to the backup directory. So then it backed the, yeah, you can see where this is going. It went on forever. It made a lot of files. But, yeah. Anyway, we'll just grep that out. Okay, we're just saying that the thing that changed should not be called .into-commit. And then we'll tap this supply. Okay, and then what we need to do is, well, there we're copying the file at the bottom. Okay, I'm using a state variable for the change ID. And then how do I actually append to a file? There's a very nice way of doing that in Perl 6. So you might have heard of slurp, which is where you read in a file. Okay, in Perl 6 we also have spurt, which is where you spurt out a file. And if you put append on there, it just means you can spurt an extra line into that file. Okay, very nice. So it's actually really hard to come up with a good name for that, by the way. Like spew is pretty bad as well. And splat, yeah, that sort of does it. Most of the words for sort of, squirting stuff out or whatever are really disgusting. So spurt is sufficiently fine if you're innocent enough. Anyway, what this is doing then is going and making those backups. Now there's one thing that's a little bit of a concern here. This almost works, but there's a slight problem. And the slight problem is that we actually have threads over in Perl 6, and the threads are happily just competing for these notifications. So what can happen is a notification comes in, and then another one comes in, and it sort of says, oh, that thread's busy processing that one. Okay, this thread can do with this other one instead. And that's normally quite a nice thing. If you were doing this with web requests, then of course it's very nice to scale over all of these CPU cores. So one request comes in, this core is busy with it, so it just sort of says to the other one, oh, go and get on with it. So fine, but for us it makes a small problem, and the problem is that this state variable here, okay, and just writing to this file and then appending to there, there's all sorts of race conditions that might come up. So tap is kind of nice if you just want to do something and it's not really an operation where you need to just have one of them going on at a time. To be safer, we can actually write it with act. Act, if you know what an actor is meant to remind you of actor semantics, which basically is an object that can only run one of its methods at a time, okay, but does so asynchronously. So act is making sure that we only actually run this block of code one at a time, okay, so we don't get any issues. So that's very nice. We can just, with a short change, actually make this nice and safe over the different threads that might be working on it. Okay, so that's how we can build a little backup tool. The rest of it is just wiring it together. So I put it into a class. I might want to have a log of things. So remember the log I had before. Sometimes if you just have a sort of log thing and you just want people to be able to, tap it if they're interested or just throw the data away if they're not, you can actually just expose it as a supply. Okay? And I put of course, the code to watch head into a private method and the code to watch the directory into one as well. So all I need to do at startup is a main method, and if we pass watch, okay, we'll just check that we're in a Git repository by checking that that directory exists, and then we just make a .intercommit directory, and we start the watcher, and then I just tap the log, okay, and say whenever we make a log entry, say it. It's kind of nice because if instead you decided you wanted to write that down to disk, or you wanted to log it to a database or something, you could just tap it and do something different. So it's a nice way to loosely couple these different things in your system. Then finally we sleep, and we don't say how long to sleep, which means we sleep forever. Okay, which of course the main thread can happily do. It can do that very cheaply, and all of the notifications go off into the thread pool and just get processed on some thread or other. So the whole program is relatively short. Okay, the list and show are just other candidates of the main method. It's actually not too bad to build these sort of sub-command style interfaces, just using writing the different main methods there. Okay, so I don't want to go too far into that, but you can see that this program was not a whole lot of code. Okay, it's fairly compact, and we even managed to factor it into a class and use some of the nice features for command line things. By the way, what happens if I just say intercommit? I have to show you this, it's kind of cool. It comes back and it actually tells me, I wrote a crappy batch file to call it, which is why it's got the full path in there. It actually tells me all the ways that I can use the program. I don't have this in my program, it's generated automatically for me by it introspecting my main methods, my main subroutines, okay? So I get that for free. I like that. Okay. So that was sort of all right, but the thing about it was that we only had one sort of asynchronous things. Okay, we just had file notifications. So I'm going to do one final example where I will show you a slightly different way of doing things. And at this time I want to compose together 3 different kinds of asynchronous data. I'm going to have events from a user interface, I'm going to have time, and I'm going to do some computation on a thread in the background and juggle all 3 at once. So what am I building? I'm building a wonderful little code golf assistant. Okay, so in here, you know, a code golf, right? You try and make the thing work in the least characters possible. So as I type in this text box here, I want my number of characters, okay, to change. There we are. So this is going to change automatically just as I type. It's going to react to those events. And here I want to just have this ticker every second showing me how long I've wasted of my life golfing Perl code. And down here I want it to automatically run the code in the background and then just show me the result. Okay, so I don't have to click run, I just hesitate typing for a moment and it automatically runs the code. So this feels like it should be simple, right? I mean, you know, it's an easy to describe application, and if you just told anybody about this, they'd be like, yeah, that sounds like an easy thing to do. So let's see how hard it actually is. Well, first of all, we need to just build up the UI. So we'll use this little GTK simple app module, and we'll just make ourselves, you can remember the UI, okay? It's a text box, a label, a text box. So there we go, okay? Well, it's a text view actually in GTK. So we make one of those, and what I'm doing on the left there is just assigning each one into a variable so I can talk about it later. And I'm putting them all into a vertical box which lays them out nicely for me. Okay, so that's my UI. Okay, now, what next? Let's do the easy thing. So the really nice thing about this little module is that it exposes user interface events as supplies. So I just need to tap the supply. So what I do is I take the supply of events when the source code changes in the text box, and I tap it, and then all I need to do is get the number of characters that are in the text box and shove that into the text of that char's label. Okay? So that means that as let me just run over to my VM. Okay, here we are. And let's run this thing. Okay, here it is. A little small actually on the screen, but just resize it here. Okay, so if you see that number 0 there, and as I type stuff in, okay, you can see that it's changed and there's 5 characters there. All right. So that was the easy bit. Okay, just UI events. What about time? Well, here things get a little more difficult because, of course, we can't sleep on the UI thread or something. So we want to do something with timers, but this timer, okay, the way they work is they basically run by default over on the threads, the thread pool. Okay, so this tick is going off in a thread. If I just update this label from some thread, it will get very, very, very upset with me. So what I need to do is somehow get it to run this tap closure on the thread of the user interface. How do I do that? Well, underneath all concurrency in Perl 6 is a concept of schedulers. Schedulers are at the heart of everything. So all of the various concurrency features, not just supplies, but promises as well, basically rely on a scheduler mechanism. And a scheduler is actually relatively simple. It's something you give a piece of code to. Maybe you ask it to run it in a certain amount of time, or at a certain time, or every so often, or as soon as possible. And it just figures out a way to do it. Now, the default thread pool scheduler is just going to have a load of threads, and whenever you give it some work, it will figure out just put it on a thread. But the alternative one that I wrote for this module is GTK simple scheduler. And what this does is it takes the piece of work you give it and magically injects it into the GTK event loop. Okay? So that this magically lets you just push any bit of work over to the user interface after doing stuff on a thread. And all we have to do is say, take this, schedule it onto the GTK user interface, and then we just update the label with the sex so far. Okay, the last piece, the last feature. Running the code on a thread. So, one problem that we need to deal with is that, of course, the user is here typing in the text box. And we can actually just sort of tap the thing and do this. Okay, this is a simple solution. So we try to eval the text they wrote, and if we fail, then we just use the default OR thing there and just pull the message out of the exception object. But this sucks in two ways. It evaluates it for every single keystroke. Okay, so if I'm halfway through typing a subroutine name, of course, it's going to fail until I finish typing it. But it also evaluates it on the UI thread, which means if it takes like a second to evaluate, then we just sort of block the user interface up, and that's kind of annoying as well. So let's first of all fix the problem that we had with making it stable. So that method is actually called stable now. I thought I updated this. Anyway, basically what this does is it makes sure that we haven't got a change to this value for 1 second. Okay? So the value is the same for a whole second, and then it passes it on. So what we're doing here is we're just saying wait until, if the user keeps typing, okay, and they stop, and we wait for a second to elapse, and if they don't type anything else, we say that's a stable value now, pass it along. Okay, so we do that. Then we have the threading bit. Okay, now threads are kind of like, you know, a little bit fraught with danger. But actually, if you think about what we want to do, we need to take this bit of text, we need to actually get it evaluated on another thread, and then we want to somehow be able to get the result back to the user interface. But if you remember all the way at the start of the talk, I told you about the autocomplete problem. Okay, the problem where the user types something and we start evaluating it, and then they change the program so it runs quicker, and the quicker version completes before the slow one does. Okay, and then we have to make sure we don't show the result of the old piece of code. So, how do we make this work? Okay, well, first of all, let's run it on the thread. So if you do .start, what it actually will do is it will take this piece of code, it will schedule it on the thread pool, and it will only push the result out once it's occurred. Okay, so that's how we can run code on a thread from a user interface event. This is really cool, because basically what we've done at this point is just transition to threaded programming with one method call. Okay, so that's running on the thread, and then what we need to do is, of course, think about the result. But let's just ponder what's going on here for a moment. Because start does not actually just give you back the result. What start actually gives you back is a supply. Okay? And the one result is going to come into the supply. Now, this is where it gets kind of funny, because what we've actually done here is we've turned our supply of bits of program into a supply of result of evaluating the program. Now, at first that sounds crazy. Okay, why do I want to do that? But here's the pretty bit. Migrate. What migrate does is it takes a supply of supplies, that is an asynchronous source of asynchronous sources of data, and it moves between them. If you think about it, what it means is that the user types something in the text box. We start a bit of work on another thread, evaluating it, okay? And what we immediately get is a supply, representing that bit of work. And migrate will immediately tap it, okay? And if it produces a result, it will just pass it along. But suppose that the user types something else in the text box, we're stable for a second, okay? Then a new supply will be pushed into migrate, and migrate will say, oh, I'll migrate to paying attention to the new one and ignore the old one. Okay? So what we get is these results, okay, without all of the risk of getting old data. Then we shove it back over to the user interface thread with schedule on. Okay? So all the hard work happens on the thread pool, and then just at the last minute we go back over to the user interface and we put the result in the text box. Okay? And we're done. So there. Let's maybe M again. There. Okay. So in here, okay, if you just watch as I type. Okay, it's not until I stop typing for a moment, okay, that it will actually go and actually evaluate my code. And of course, if I put a syntax error into here, okay, I get that down at the bottom. But if I just go and put something else in there, then now it compiles and just instantly that result pops up. Okay, so this is all working kind of nicely. And if I was stupid enough to do something that took a very long time, and then I was to change it to something that was quick, okay, now I won't get the old result coming and scribbling over the later one. Okay, so finally, the way that we actually run this program is we just do .run, okay, and then we start running in this thing. And one of this point you might realize is that we have 29 lines of code that actually fits in a gist on GitHub in one screen full, doing all of this. Okay, so in 29 lines, I have a program that does user interface events, time, multi-threading, avoiding race conditions. Okay, and it's just little bit of code. In fact, I guess I have it. Just to show you it. Okay, that's the whole program for the cold golf assistant. Okay, that's it. So not too much going on in that. But I think some genuinely, traditionally tricky problems solved in quite an elegant way. I probably am out of time, but I just very quickly wanted to point out something about the GTK simple module. And that is that there's no XS code or C code that we've written. And all of it is done using a native call module. So basically, native call lets you just express that you want to have this, say, GTK widget show function, and it's from the GTK3 SO library, and that's all you have to do to actually be able to call C code. So here, this is really cute. What we're actually able to do is call this gsignal connect. We can pass a Perl 6 closure to a C callback function, okay, and then all we do is just map it into the supply, okay. So we just do s.more on this, and that's how we expose the user interface event. So that's kind of a neat way of doing this, okay. And this is calling straight down to the C code, so I don't have to write any C binding myself. Even integrating with the GTK scheduler is something that we can write in Perl 6 code. I was actually quite amazed by that. The thing that scared me most was that it worked the first time, and I spent the next 10 minutes wondering why it was pretending to work, but it turns out I actually got it right. So, yeah. Okay, so just to wrap this up a little bit. Asynchronous programming has traditionally been kind of difficult because we have all of these, this bits of data just arriving whenever they please, interleaved as they please. And traditionally, we've sort of used mechanisms that don't let us compose interesting and complex programs out of them. I think reactive programming gives us a way of essentially making asynchronous data a lot easier to tame. And it does it just in the same way that things like grep and map make lists easier to tame. Okay, by factoring out the repetitive bits of flow control, it's just that with asynchrony, the factoring out is even more valuable because we can factor out all lots and lots of nasty things like dealing with time and race conditions and synchronization between different threads. So we can pull even more into these. So of course the implementation of things like map and grep is a little more involved here. The implementation of things like zip is a lot more involved because the data can arrive from 2 threads at once, and we need to zip it together. So they're a bit more work to implement. But the goal really here is, for me, to make the easy asynchronous things easy, while keeping, of course, the hard asynchronous things possible. And I think this is a nice step towards that. Okay, so if you're curious to explore the code, I shoved it on GitHub there. Okay, so it's sat waiting for you. That's how you can hunt me down after the talk. I'm here all today and all tomorrow as well. So we'll be happy to discuss anything then. I guess I'm kind of out of time. Nobody said anything. That means I could do one question maybe.
Can you explain once again, because you said that in that example we dealt with the race conditions at some point. Remind me once again where that, at which point we dealt with it.
It was migrate. It's migrate, okay? Migrate takes, it's essentially a supply of supplies, okay? Which sounds kind of weird. But what happens is each time we start running a piece of work on another thread, then we have a supply representing the result, okay? And what we know is that the value the program produced will be thrown at us through that supply. Now, when we change the value in the text box, it makes another supply and gives that to migrate, and migrate ignores values from the previous one and starts just looking at the latest one. If we're to change it again, okay, it'll just start looking at that latest one again. So what it means is that we have essentially new data sources arriving asynchronously, okay, as the user changes the text box, and migrate means we only pay attention to the latest available source of data. Okay, does that help?
It helps, but I thought that we were talking about race conditions, there would be some kind of stacking if we didn't do that. And in this case, if we didn't use migrate, the application wouldn't get stuck. We would simply get incorrect results, right?
Incorrect results can come from a race condition as well. I mean, race conditions don't just mean deadlock. They can lead to incorrect results. So yeah, there's not a deadlock risk here, just like there wasn't when the user was typing in the autocomplete search box. But there is a race condition and a chance to do something wrong and get out of order results or something like this. So yeah, it's a race. It's not a deadlock risk, but it is a race. Anything else?
Yes.
Please.
The native core module you used to create the GTK simple module, does it work whatever the backend you use for PL6?
Yes, I haven't actually tried running this code on the JVM, but it should work in that it supports callbacks as well. I was running it on more VM here, which has much faster startup time, which is why the app loaded in not long. And it definitely works there, so you're slowly running it. Probably works on Parrot as well, because we did callbacks there too. So generally native call is pretty portable. There's probably the odd quirk. I think you found one, Ted, doing the game stuff.
It's about exporting, and I don't think there's an exporting here.
Oh, okay.
Okay, so
Okay, and that might not even be a bug in the native calling itself, then it might be in something else.
Yep.
So, yeah, but the goal is consistency over all the backends for native call, and the test suite passes in full on all the various backends for native call now. So, yeah, you can write this once and then take it and do it on the JVM, and it should work out. Yeah. Okay, and probably it's lunchtime, so
that's right.
yeah, okay, well, eat well, and dziękuję.
So,